我们现在是礼拜四晚上7点到9点，也很高兴大家在周间的晚上能够参与这个很难得的活动，因为我们今天请的是真的是第一线的科学家，因为我们现在有一个国际的会议就在科普馆办，他们就是实际上去拍出黑洞，而且实际上去做黑洞的这些资料处理的真的科学家，是真的人，好，不是神话故事里面出现的。所以这是目前这2个小时最后2分钟会用中文的时候，里面每个 slides 都有英文，但是如果后面有问答的时候，你们可以问中文、问英文都没有关系，我们会有专人帮你们翻译。So now it's the English time, so we are happy to invite our 2 speakers here. One is Fumie-san from Japan. Yeah, everybody. The other one is a French astronomer, and now it's a professor in Mexico. Welcome to Laurent. Okay, these 2 speakers will give I'm pretty sure it's a fantastic speaking here. And we have a lecture from the 2 side by side. So the first one, we introduce Fumie-san. You start. Okay.
So thank you for inviting us today. We are very happy to getting this chance to talk here. So today we will tell you that how we mean Event Horizon Telescope collaboration, how we get the first black hole images. So let's start. So let me start from this. What is a black hole? What do you think of when you hear the word of black hole? Any opinions? So maybe you imagine that black hole will suck in everything, and you never escape when the black hole suck you in the black hole. Or you may think that the black hole might be a gateway to another world. What do you think of? So I will start from the history. More than 100 years ago, Einstein developed a theory of general relativity. He might have said, I guess, I developed a theory of general relativity. If this theory is correct, then light passing near heavy objects should be bent. In response, Eddington and his team observed the evidence of this light bending. So they might have said, indeed, when we measure the position of stars near the sun during a total solar eclipse, the locations of stars have changed. This is as calculated by general relativity. So why if we observe the star position, then we know the evidence of the general relativity, so light bending. Then let's think this condition. So if we observe this star, usually the light from star goes straight and enter the telescope. Then we can observe it. But in this case, this is not true. If the path of the light is close to the sun, then the light will be bent like this because of the general relativity. So we cannot observe this light. But then, how do you think how we can observe this starlight? The answer is this one. So the light goes away from the sun and bent then the light will enter the telescope. So we can observe this. But so the observer, we can see only the direction of the light. So the direction is here. In this case, we look the star move away from the sun, like this. So if we observe the stars, this is a schematic view of our observation. So if there is no sun here, then the starlight goes straight to the observer, so to the telescope. But if the sun is here, the light bends like this, then the stars move away from the sun, so like this. So therefore, if we observe the location of the stars during the solar eclipse, then we can get the evidence of the general relativity. And on the other hand, based on the general relativity, Schwarzschild calculated that the general relativity, then he found that there can be strange celestial objects of intense gravity from which nothing, not even light, can escape. That is black hole, but the actual use of the term black hole began in the 1960s. So at that time, they did not use the black hole, the word black hole, but yeah, he found the black hole in the general relativity. But Einstein did not believe that. So at that time, no one knew that whether the black hole exists or not, really exists or not. What do you think? Is the black hole there in the universe? What do you think? Yes, thank you. So, yeah. So in 1971, astronomers found a stellar mass black hole. Stellar mass black hole means a few tens of solar masses, and they found a very X-ray bright object in the universe called Cygnus X1 by using an X-ray satellite, UFR, US satellite. Yeah, and the source was fluctuating so violently in a short period of time. So astronomers thought that this object, X-ray object, is black hole. This is an imaginary view of the black hole, and this is a black hole and a star is attracting each other by the black hole gravitation. And the atmosphere of the star was stripped away from the star and sucked into the black hole, like this. Yeah. And on the other hand, from the vicinity of black hole, jet, this is a plasma outflow, very high speed outflow, is ejected from the vicinity of the black hole. This is a standard view of the stellar mass black holes. And on the other hand, there are some supermassive black holes in the galaxies. So from the 1940s, astronomers found that some very bright core galaxies. So galaxies, at the center of galaxies, there are many bright core, and this is called Cepheid galaxies or quasars. And the bright holes are called as active galactic nuclei, AGNs, which emit intense radiation at the center of the galaxy. In the late 1970s, it came to be believed that AGNs are phenomena that radiate enormous energy when the surrounding gas is sucked into a supermassive black hole. So this is one example of active galactic nuclei. This is an elliptical galaxy of M87. This galaxy is very large. And these bright points, each bright point shows the stars of galaxies. And especially bright spot is here. This is an AGN. And at the center of this AGN, it is believed to be a black hole here. And from the nuclear jet, so out from the black hole is ejected with high speed, very high speed. And here is an imaginary view of very vicinity of the black hole. There is also a black hole and disc-like gas, disc-shaped gas, which sucked into the black hole and ejecting the jet outflow. This is a standard view of the supermassive black hole and AGN. The next one is there is also a supermassive black hole at the center of our galaxy, so Milky Way galaxy. And Genzel and Getz respective groups have been making long-term observations, and they measure the motion of the stars here in the center of our galaxy. So this has revealed that at the center of the rotating star is a black hole with a mass of 4 million times that of the Sun. So Genzel and Getz were awarded the 2020 Nobel Prize in Physics for this work. And I told you that about the observation, black hole observation with electromagnetic waves, like visible light or radio waves and X-rays. But we can also observe the black holes with gravitational waves. This is totally different from the electromagnetic wave. And LIGO detected the first gravitational waves in September 2015. These gravitational waves were caused by the merging of two black holes. One is 29 and the other is 36 times the mass of the Sun. The result of this merger was a black hole with 60 times the mass of the Sun. So far, I presented many observational results of black holes, and we know very well about black holes with these studies. But can we see the black hole? Not yet. Not yet. We cannot see the black hole yet. So we would like to know that how we can see the black hole. So how does it look like? So apparent black hole, around the black hole, space-time is greatly distorted due to the effect of the general relativity. So light that gets too close to the black hole is greatly bent and sucked into the black hole, so never escape. On the other hand, the observer can see the light close the black hole. So light will go this way. So this is the orbit of light. So if we see the black hole, then we can see the ring shape because of the strong gravity. The light bends strongly. Then we can see this ring shape. This is called photon ring. And at the center of photon ring, black hole should be there. And so we see the ring, and inside of the ring, there is a black area. It calls black hole shadow. So if we observe the ring, photon ring, and the black hole shadow, then it should be evidence of the strong gravity of black hole. So, yeah. So we can see the black hole as a photon ring and the black hole shadow, but we could not see the black hole but 10 years ago. Why we cannot see the black hole? It is because of the apparent size of the black hole is too small. So I would like to explain the size of the black hole. So the black hole radius is defined as this equation. Yeah, and G is a gravitational constant, and C is speed of light. So they are constant. So radius is only depending on the black hole mass. And the size of diameter of the ring is defined by this 5 times radius. So this diameter of ring is also depending on the black hole mass. And to see how large the black hole is in apparent size, not only the actual ring size, but also we need to know the distance from the black hole. And if we see the black hole closely, then it should be large. And if we see the black hole at a distance, then it should be small. So you can imagine the giraffe. Have you seen a giraffe in a zoo? Zoo? Yeah? No? Yeah? Have you seen a giraffe? Oh, thank you. Thank you. Thank you. If you see a giraffe in zoo, it should be very tall, so large. But if you see a wild giraffe, have you seen a wild giraffe? No. So if you see a wild giraffe in a savanna, it should be very small. You can imagine that, right? So black hole, if we see the black hole very close, then it should be large. Usually black hole is very far away, so it should be small in apparent size. So let's see the black hole size. So there are two largest black hole in the universe in apparent size. One is Sagittarius A star. Oh, wait. Sagittarius with A star. This is located at the center of our galaxy. And another one is M87 supermassive black hole. And their masses are 4 million solar masses and 6.5 billion solar masses, respectively. So we can calculate the ring size with the previous equation. Then 6 million kilometers and 90 billion kilometers, respectively. On the other hand, the distance is 26,000 light years from the Earth and 55 million light years, respectively. So So the ring size is 3 orders of magnitude larger for M87, and 3 orders of magnitude further for M87. So the apparent size is almost same, 54 microseconds and 40 microseconds. Microsecond is a unit of angle. 1 microsecond corresponds to 4 billionths of degree. In other words, the apparent size of the black hole is 100 millionths of a degree. So small. So this is corresponding to see a tennis ball on the moon. So how do we photograph this so small object? So I will pass the mic to Laurent.
Thank you. Good evening, everybody. So, as Fumi-san explained to us, astronomers think that black holes exist in the universe, and we also know where they are. They are at the center of galaxies, for instance, and we know what they should look like. We know that there should be regions where we see a bright ring, the photon ring, surrounding a darker region called the shadow of the black hole. So what are we waiting for to make an image, to take a photograph? Should we all take our cell phones and try to take a photograph of the black holes? Do you think that would work? No, unfortunately not. And the reason is because of this. It's because black holes, although they are big objects, by human standards, they are very big, 90 billion kilometers or 60 million kilometers. This is about the size of the solar system. They are also very far away, so they are very small apparently on the sky. They are the size of a tennis ball on the moon. Or I like this other analogy, they are the size of a single atom in my finger, seen from my eyes. A single atom in my finger at 1 meter, this is about the size of these black holes on the sky. So this is the difficulty. How do we make observations of these black holes to obtain an image? So what we need is a big, big, big telescope. Because telescopes, the bigger the telescope, the better the angular resolution that it obtains. A bigger telescope will see a finer image of the sky. So if we want to make an image of a black hole that allows us to see the ring and the dark region, we need a telescope the size of the Earth. Well, that's complicated, right? How do we make a telescope the same size as the Earth? How do we do that? So the answer is that we cannot make a telescope the size of the Earth. This is impossible. We don't have the technology to make a telescope the size of the Earth. It would be too complicated, too expensive, and we simply don't know how to do that. But we can use a technique called interferometry. So I'm going to try to explain just a little bit how interferometry works. So in principle, when you have a telescope, like this telescope, and you're looking at the sky, the light that comes from the sky will bounce off of the telescope and then will be focused to this second point called the secondary mirror, and then it will focus and it will make an image here at the center of the telescope, for instance, an image of a black hole. But in reality, we don't have to have a complete telescope like this. We can replace this telescope by many smaller telescopes that are distributed, along the shape of the bigger telescope that we want to synthesize. So instead of making one very, very big telescope, we can combine many smaller telescopes and then reproduce, but in a computer instead of in reality, reproduce what a real telescope does by combining, for instance, the light that enters here, it is reflected there and then it goes there. And the light that's coming here reflects here and then goes there. And then the two light rays combine to form the image. So what we are going to do is we are going to place a little telescope here and another little telescope there. The two telescopes are going to observe the same source. And what normally would happen here to form the image, we are going to make in a computer. So we are going to build a computer telescope instead of a real telescope. Now that's complicated, and it involves a lot of electronics, you know. So each telescope will have a receiver, a receiving system that will register the light rays that come from the source. And this is going to enter a gigantic computer that's going to transform the light into electronics. And then this is going to be written in these boxes here. Each of these boxes is a big computer disk that contains a lot of data. This is about the size of a person. This is about 2 meters high. And each of these little white boxes is a jukebox of disks where the data are going to be written. At the same time that we observe, we are going to also have an atomic clock that will be writing data also on those disks so that we can later combine the data and form an image. So the Event Horizon Telescope is using this concept. It's an array of 8 telescopes. They are shown here as these little circles on the map of the Earth. The 8 telescopes are located in Hawaii, in the United States of America, in Mexico, in Chile, at the South Pole, and in Spain. They are covering the entire Earth. So it is as if we were generating a telescope the size of the Earth, the complete Earth. The separation, the maximum separation between the telescopes is about 8,000 kilometers, you know, between, for instance, the South Pole and Mexico, or the South Pole and Spain. As I said, each of the telescopes is equipped with an atomic clock that will write the tick-tack on the disk, so we can then combine the data. And the signals are recorded at each station on these disks. This is another view of the Event Horizon Telescope. So there's a telescope here in Spain, another in Greenland, I will go back to that later, in Hawaii, in the United States, in Mexico and in Chile, and at the South Pole. So it implies a lot of people, because we have to have a group of astronomers going to each telescope to do the observations. So here are pictures of astronomers at various telescopes. This is, for instance, the group of astronomers who went to observe at the Mexico site. The Mexico site has this very big antenna. It's about 50 meters in diameter. This is another group of astronomers observing at the Spain site. In Spain, the telescope is about 30 meters, and the same happened at all 8 sites. So about 40, 50 astronomers were involved in the observations, so that each telescope could observe simultaneously. That produces a lot of data. So here is one of our colleagues. He's called Lindy Blackburn, and he was at the Mexico telescope. And these things that you are seeing here are precisely, you know, the white things that you were seeing in this rack before. And as you can see, they are made of 8 computer disks. And this disk would fill up during the night with all the data that we're collecting at all the telescopes. There's about 1 petabyte of data in these data disks. And that's only about half of what was collected in Mexico. The same was collected in Hawaii, in Spain. So that's many, many petabytes of data, a lot of data. And these disks, they are then put in a large box, and they are sent by plane, to a central computer, where the disk will be read and to form not quite an image yet, but a quantity that can be transformed into an image. So this is one of these large computers. Again, all of these are these disks that I was talking about. And here they are all connected together. They are combined, the data are combined to form a quantity that will then be transformed into an image. So during the all the black hole images that we have published so far, some of them are here in this museum, you probably have seen them. They were obtained in 2017, and these are the observations that were made. In addition to Sagittarius A star and M87, that were the 2 black holes that we were interested in, we also observed a number of other sources with weird names like 3C279, Centaurus A, this weird number, and NRAO 530. And those observations were also published in the recent years, in 2020, 21, 22, etc. Although there's also black holes in these images, but we don't quite see them. We are not quite able to resolve them yet, but they were observed at the same time as the other black holes. So now, Fumi-san will explain to us how we make images out of these observations.
Thank you. So let's move on to the imaging of the black holes. So you may think, why it is so difficult to make an image of the black hole? Or, so this interferometric data. If the telescope for visible light, then in the case of the visible light telescope, not so difficult. It's almost same as taking a picture with your smartphones. Almost. Not exactly same, but yeah. On the other hand, our telescope, so very long baseline interferometer. In that case, we observe with each telescope, and after the correlation, we get data set like this. This data set is a Fourier component of the image. Fourier may be difficult, but yeah, some data set. And using this data set, we reconstruct image. We reconstruct image from this data set. If we use telescope, many telescopes we can use, and densely the telescope is located on the Earth, then we can get a very dense sampled data set. Then we can get image easily. But in reality, the telescope is located on the Earth very sparsely, so the data set also sampled sparsely. Then the image become very difficult. So to overcome this difficulty of the imaging, we developed developed many imaging tools. So today, I will not explain details of the imaging tools, but in the developing, we tried many times of imaging challenge. I would like to explain this today. So in the imaging challenge, we assume like these objects are in the sky, and we observe these objects with EHT. Then we can obtain some data set, not real, but just calculated data set. Then we can try with this data set to make an image with the developing tools. This is the imaging challenge. In 2016, we did like this imaging challenge, and this is one example, snowman. So you can imagine a snowman on the sky. And we observed that snowman with EHT. Then we get this data set. And only the person who made this data set knows the answer. So the answer is snowman. But we, so imaging team, did not know the answer. So blind imaging. We only received this data set. And we did not know what is the answer. Then we reconstruct the image like this. So I hope you see there looks like snowman. So we successfully obtained the answer from the blind data set. Then we get the answer will be maybe snowman. We knew that. So we did like that things as an imaging challenge. Before the observation of EHT, we tried and error, then we developed the imaging tools like this. And in the real observational data, we observed M87, supermassive black hole, and Sagittarius A star in our galaxy. And we observed them. And we also have difficulties to make an image of these objects. In the case of M87, this is the first attempt to capture a black hole in human history. So we need to make an unbiased result. So, of course, we know that it should be ring, but we never make ring image intensely. So we need to be unbiased, very independent. So it's a difficulty in the M87 image. And in case of Sagittarius A star, please play the animation. It is difficult to image the object because the structure changes over the 10 hours per observation. So VLBI imaging assumes that the source structure does not change during the observation, but this source changes so quickly during the observation. So this is a difficulty in the case of Sagittarius A star. So in the case of M87, we would like to make an unbiased image. So we divided our imaging members here. We divided into 4 teams. And each team performed the imaging completely independently. So without sharing any information with each other, and without sharing any information with outside of the team. Then we get these images independently. And they are all consistent with ring-like structures, and southern side is bright. So we are happy to get a consistent image independently. And this is the final result of M87 image. If we see the Virgo, and there is an elliptical galaxy M87 in the Virgo. Maybe this one? Yeah. This is very large elliptical galaxy, and each is a star light. And at the center of this galaxy, there is an AGN and an ejecting jet. And at the center of the galaxy, we could see a black hole here. This is our result of M87. On the other hand, in case of Sagittarius star, so play the movie, please. Yes. So again, the structure changes quickly during the observation. So this is the difficulty of the imaging. So at this time, we aim to reconstruct only an average image, not movie. The movie is very difficult to reconstruct. So we start from an average image. And result of image. So imaging results are here. We reconstructed thousands of images with many imaging parameter sets. And we knew that all images are divided into four groups of the image. So this type, this type, this type, this type. Slightly change, but three of them are showing the ring structure, ring-like structures, but bright points are different. And these are the distribution of each team has. So how many images are included in each team? So many of the thousand images showing the ring structure. So we are happy. And we get the final image by averaging these images. So again, I show the movie here. So Sagittarius star is located at the center of our galaxy. So we see the center of Milky Way. And in the Milky Way, there are many stars here at the center of galaxies. And furthermore, at the center of the galaxy, some stars are rotating around something. Yeah. And at the center of them, the Sagittarius is the black hole here. Yeah. So this is our second result. Thus we successfully made images of two black holes. So what we know from these images? Then Laurent will explain that.
Okay, so these are the images of the black hole at the center of M87 and the black hole at the center of our Milky Way. So what does it mean? What does it tell us? What do these images tell us? And what else can we do about black holes with these kind of observations? So the first thing that is important is that the shape, the image is exactly what we expected that we would see. As Fumi-san explained, we expected to see a ring of emission associated with, in particular, the photon ring, surrounding a darker region that is called the shadow of the black hole, and it's a region that happens because the light that should come from that direction is absorbed by the black hole, is captured by the black hole. So we don't see that region. This region appears black, or at least dark, because all the light that should be coming from here is captured by the black hole. And Fumi also told us that we know the mass, we know how many million solar masses there are in the black hole at the center of the Milky Way. We know the mass of the black hole at the center of M87, and from that we can calculate how big this dark region should be. And she showed us that we expected 54 micro-arcseconds for Sagittarius A star and 40 micro-arcseconds for the center of our Milky Way. These numbers, they don't really matter, they just are very, very small, but we know what they are, you know. We know exactly that this is what we should be observing. And in these images, we can measure the size of these regions in the true image and compare our results with what the predictions, the theoretical predictions tell us. And these are the measured values. So we observe where we expected 54, we observe 52, but with an uncertainty of 2. That is, it could be 52, it could be 53, it could be 51, it could be 54, it could be 50. In other words, this is exactly consistent with the theoretical prediction. And the same happens for M87. We expected 40, and we measured 42, but with an uncertainty of 3. So once again, the measurement is perfectly compatible with the prediction, the theoretical prediction. Now this is very important because it tells us that the physical theory, general relativity, that we believe describe these objects actually works, because in order to calculate these numbers, we use that theory. If the theory was wrong, it would have predicted something wrong, something different from what was observed. The fact that what we observed is perfectly consistent with the prediction tells us that general relativity works. And this is very, very important because around black holes, gravity is extremely strong. These are very unique objects in the universe where gravity is much, much, much stronger than on Earth, and so strong that we cannot reproduce these kind of conditions in laboratories on Earth. So black holes are the only objects in the universe where we can test this theory of general relativity in the presence of such a strong gravitational field. So in principle, it could have been that, you know, general relativity would not have worked, but it does work. So it's a beautiful confirmation that general relativity works, and Einstein can be very proud because, you know, he predicted, or his theory predicted 100 years ago exactly what we are observing now. And his theory predicted 100 years ago what we are observing now, when 100 years ago we had no way of, you know, knowing that this would be observable. So this is a beautiful confirmation. And again, this is the reason that we are seeing this structure is because of this effect that Fumi explained, that if there is a black hole here at the center and light is produced around the black hole, we should see this bright region surrounding a darker region at the center. And this is exactly what we are seeing in the observations. Now, not only Einstein is right, but he was right twice. right? He was right for the size of the black hole at the center of our Milky Way, and he was right for the size of the black hole at the center of M87. Now, these two black holes are actually quite different. One is about 2,000 times more massive than the other. And according to Einstein, according to general relativity, the only thing that changes when you make a black hole more massive is it makes the black hole larger proportionally to the mass. A black hole that's 2,000 more massive should also be 2,000 times larger. But other than that, they should look exactly the same. They should just look bigger, but have the same structure, the same shape. And again, this is exactly what we are seeing. If you didn't know, you could almost think that this is M87 and this is such a star, right? I mean, the image looks exactly the same. A black region at the center, the shadow, and a ring, a bright ring around the shadow. And the two images are exactly the same. Yes? And this is again something that Einstein predicted, that they should look exactly the same. Now, why do they look so similar? Well, so the reason is that although M87 is about 2,000 times more massive than such a star, it is also about 2,000 times farther from the Earth. And so the black hole, the size of the black hole in M87 is 2,000 times larger, but it's 2,000 times further, and so they look exactly the same on the sky. But that's an illusion, right? In fact, the black hole in Sagittarius A star is much, much smaller than the black hole in M87, right? So the black hole in Sagittarius A star is only at 27,000 light years from us, whereas the black hole in M87 is 55 million light years away, 2,000 times farther. But in actual size, the black hole in M87 is much larger. So this is, just for comparison, this is the image of the black hole in M87. This is the image of the black hole in Sagittarius A star. And just for comparison, the size of the solar system is shown here. So here is, it's for comparison. Of course, the black hole is not centered on the solar system. It's much farther away. But just for scale, so this is the sun here, and this is the orbit of Pluto. And so this is roughly the size of the solar system. So as you can see, the ring in M87 is larger than the solar system. It's a fairly large object, right? This is Voyager 1. This is a man-made satellite that was sent many years ago, and it has now exited the solar system. And it just arrived at the same distance as the ring in M87. So M87 is larger. The shadow in M87, the dark region in M87, is larger than the solar system, right? In Sagittarius star, on the other hand, this is where the sun is, and this here, this circle here, indicates the orbit of the planet Mercury in the solar system. Mercury is the closest planet to the sun, okay? So what this shows is that the entire ring in Sagittarius star would fit inside of the orbit of Mercury, right? Whereas in M87, the entire solar system would fit inside of the ring. So it shows that M87 is much, much larger than Sagittarius A star, right, intrinsically. But it's also much farther from us, so they look like they have the same size. So now, the collaboration to understand these images and analyze these images, the Event Horizon Telescope collaboration has made a lot of theoretical simulations of what a black hole should look like. And the idea is to try to see, if we can make models, theoretical models that, you know, if we observed them with the Event Horizon Telescope, would look like the image that we are actually seeing in M87 and in Sagittarius star. And the answer is yes. So this is one example. This is the actual image of M87. And this here is a model, a theoretical model made in a computer, where you have a black hole at the center, and then you have material rotating around the black hole at very, very high speed. And this material also produces a magnetic field, which then generates light, radiation. And so this is what this object would look like if we had perfect vision, right? But when you look at this object with the Event Horizon Telescope, you would see something like this. It's a little bit more blurry because, you know, the Event Horizon Telescope has very, very high angular resolution, but not perfect angular resolution. And so these models, the conclusion is that these models can reproduce perfectly well what we are actually observing. So now, what is next? What else can we learn about these black holes? So there is one thing that we would very much like to know about these black holes, and it has to do with the fact that these objects that Fumi was telling us about, the galactic nuclei, active galactic nuclei in galaxies, like in M87 for instance, they usually emit a jet. So this is an image in the radio image of M87, the same jet that Fumi was showing us earlier. This is the center of the galaxy here, and there is this jet coming out at very high speed. It's also visible in the optical, in X-rays, in many other wavelengths, but here it's in the radio. And these jets have, this is now a zoom, the bottom image here is now a zoom on this part of the image at the top. And you can see that these images are very interesting structures, sort of like a little helicoidal motion. And many black holes produce these kind of jets. It's almost a signature of the presence of a black hole to have jets. So the question is, how do they do that? How is it that black holes produce these jets, so that the presence of a black hole makes it happen that you see a jet, right? So the connection between jet and black hole, we know it exists. We know that when there's a black hole, there's almost always a jet. But we don't understand how the jets are produced, how they are formed, how they are accelerated. And so this is a very interesting question, how it happens. And M87 is probably one of the objects where we could best try to understand this problem. And there's been work very recently by colleagues of the collaboration making very high resolution images of M87 that shows the central black hole. In fact, you can see the ring structure here in the black hole also in these images, and the jet coming out of the black hole. This is still not quite sufficient to understand exactly what's happening, how these jets are produced, but this is progress towards understanding this. Very recently, as we tried to explain, the Event Horizon Telescope does not make a picture, does not take a picture like a cell phone. It measures quantities, and then with algorithms that have been developed in the collaboration, these quantities are transformed into an image. And depending exactly what kind of algorithm you use to make this transformation, you can obtain different images. So recently, colleagues of the collaboration, in particular Lia Medeiros, who was actually here this week, developed a new algorithm and used it on the M87 observations, also obtained in 2017, to produce a new image. This is this new image here, which looks even sharper than the image that was produced in 2017. This is produced from the same data. that we obtained in 2017, just processed in a different way. So we'll have to be, now analyzing exactly how these algorithms work, but I think it's a beautiful image that shows even more details than the original image. So it's even a better image than the first image that was obtained. And then recently also, we obtained, that was published a few years ago in 2019, we obtained an image of also M87, but in what is called polarized light. So basically it is like looking at M87 with sunglasses and see only one part of the light coming through. And this is important because it shows us, it tells us something about the magnetic field in these objects. And we strongly suspect, astronomers strongly suspect, that the magnetic field is crucial for producing these jets that come out from these objects. So being able to characterize the magnetic fields in the surrounding of black holes is very important to understand how these objects work. And this image here shows the direction of the field from M87. And in fact, it's very important because it shows that the field is fairly strong. There's a very significant magnetic field in this object. And as you can see, it is oriented in a certain way that only some theoretical models can reproduce. Other theoretical models make other predictions. So that allows us to learn something about the physics of the gas around M87. So now, before I finish, I want to mention that these observations of M87 were very, very important for physics. This was the first image of a black hole. It confirmed that Einstein was right. It put strong constraints on how matter behaves in the surrounding of a black hole in very strong gravity. It constrains how these jets are produced in these objects. That was very, very important. And in fact, the EHT collaboration obtained many prizes, distinctions at the international level for this work. And I think more distinctions will be obtained in the future. But this image did not only have an impact on the academic community, on the science community, but also on the public in general. And I wanted to mention a few examples of this impact. The first example is that little GIF animation here at the top. This is a Google Doodle. As you probably know, Google every day on its webpage has a little animation called Doodles. And on the day in 2017 when the observations of M87 were revealed, within about half an hour, Google had made a new doodle that showed, precisely the black hole, the image of the black hole, swallowing the Google letters and then disappearing. And this was not made by the collaboration. This was made by the Google Corporation, but it was sufficiently important. The result was sufficiently important that Google decided to do that. Another example has to do with the Museum of Modern Art. The Museum of Modern Art in New York City is one of the most important museums, art museum in the world. It has a beautiful collection of modern art, expressionists and abstract paintings, very impressive museum. And the directors of the Museum of Modern Art contacted the Event Horizon collaboration asking for a very high quality print of the image of M87. And this print that was produced by the EHT collaboration and given to the Museum of Modern Art is now part of the collection of artwork at the Museum of Modern Art. In fact, it is only the second piece at the Museum of Modern Art that has to do with science and technology. All the other pieces have to do with art, right? There are paintings and sculptures these kind of things. Do you have any idea what the other science and technology piece of the Museum of Modern Art is? It's the footprint of Armstrong when he arrived on the moon. You know, when Armstrong got out of the moon lander and stepped on the moon, his shoe left a print on the dust in the moon, and he took a picture, right? So this picture is also at the Museum of Modern Art. So this is only the second and the only other science and technology picture at the museum is the image of M87. So if you go to New York and you go to the Museum of Modern Art, you might see this picture on the wall. I think that's pretty cool. I think that's very impressive. I'm French, as my accent probably reveals, but I've been living in Mexico for 23 years now. And as part of my work as a professor at the university, I also get to give lectures to you know, public in general and little kids and not so little kids. And one day I was giving a course in a primary school in Mexico, and I showed the image of M87, the same image that I showed today. And at the end of the lecture, the teacher, the physics teacher of the group of kids that I was speaking with, came and told me that that image was already in the textbook that they were using to teach physics to these little kids. They were kids about 12, 13 years old, like many of the kids here in this room today. And so he gave me a copy of the textbook. This is all in Spanish, of course, because it's in Mexico. It's a second grade textbook, physics. And indeed, there is this image of M87. And you can't read from here, but it mentions that the telescope in Mexico participated in making this image. So I think this was really nice also, that little kids in the classroom in Mexico could see the images that had been obtained just before, and know that this image was made in part thanks to a telescope in Mexico. So I think this is very, very important, that people in general and kids in particular know that. So now, just to finish, what is next? What else can we do? We have now made 2 images of black holes. You could say, well, then your job is done. You can retire, but no. We want to continue, and we are continuing. So the first thing that we are doing is we have made new observations of Sagittarius A star and M87 with the Event Horizon Telescope, but with a better Event Horizon Telescope. So in 2017, there were 8 telescopes in the array. We have now included several more, so there's about a dozen telescopes now that can participate in these observations. And we have made new observations in 2018, in 2021, in 2022, and very recently in 2023 of Sagittarius star and M87. And we are in the process of analyzing the data. In fact, that's the reason why we are meeting here in Taiwan this week. So stay tuned. There's going to be more images of these black holes published in the future. And we certainly hope that they will be as nice or even nicer than the images that we have published so far. And then, as Fumi-san also explained to us, these black holes, they are dynamical. You know, the animation that was shown shows that if you look at the black hole, it changes, right? It moves, the gas around the black hole moves. So if you make several images, you're not going to always see the same thing. You're going to see changes in the images. And it's a problem for us because that makes it more difficult to obtain these images because we have to take into account these changes. But on the other hand, it means that if we do make these images and we manage to make images with enough quality at different times, then we can not only obtain images of black holes, but movies of black holes. See how these black holes change with time. And so we have this project called the Next Generation Event Horizon Telescope that would include the existing telescopes in the array. These telescopes are already have been used for these observations, but would add about a dozen other telescopes in the US, in South America, in Mexico, in Africa, in Canary Islands here, in Korea here on this side of the Pacific, to have more telescopes, better images, and better fidelity in the images so we can make movies of black holes. So we hope that within maybe 10, 15 years, we should be able to have not only images, still images of black holes, but movies of black holes, movies of Sagittarius Star, of M87. So that's going to take a bit longer because it's hard, but we certainly hope that we will be able to do that in the future. And just to finish, I want to say that Taiwan has been very active in this work. That's one of the reasons we are here this week. And Taiwan in particular co-owns one of the telescopes that has been involved in EHT observations. It's a telescope that's in Greenland, on a base in Greenland called Thule. And it's an important telescope because it's very far north, right? So this is this telescope here. As you can see, it's the one closest to the North Pole. So it gives very, very long separations with other telescopes in the array. And because of this, it has played a very important role in making these high-quality images. And Taiwan has been a very important player in getting this telescope to work. Here is a group of happy Taiwanese engineers and astronomers after they finished building this antenna. That was, Satoki would know, I don't know exactly when this was taken, but this was taken several years ago, and since then the telescope has been operating as part of the Event Horizon telescope. And with that, I will finish my presentation. I thank you very much for your attention.
Okay, thank you for Laurent, thank you for Flumier. And now it's a question time. So either language you used, that's fine. We have the interpreter over here, and not just me, and Hongyi. Hongyi not here? Okay, I saw Hongyi. So everything, even you know nothing about the previous slides, you still can ask a new question. That's our purpose. 可以讲中文，没有关系。好，不用太紧张。Okay, so we get out the first one. So which language you prefer to use? Chinese. Oh, Chinese. Okay, cool.
How about French?
Oh, for French. Parlez français? Okay.
黑洞会有喷流，那我想请问一下，就是现在好像都只知道它其中一边，那有没有办法是拍到它另外一边
Okay. Wait, your turn. Yeah. Come on, you're the experts in black hole. You should.
I should translate. And I think Fumi can.
You should translate to okay.
Thank you. So the question is about why the black hole we show has only one-sided jet. Is it possible to photo two-sided jets?
I'll give you my answer. So the reason is because these jets, in fact, that's a very interesting question. Let me go back. The reason is because the emission that is produced by gas around in space, that kind of emission, is amplified in the direction of motion of the gas, and disamplified in the opposite direction. So what happens for this jet here is that this side of the jet is the side that is moving towards us. It's approaching us, and therefore the light is amplified in that direction. Whereas the other side of the jet, which we cannot see here, but it exists, we just cannot see it, it's moving away from us, and that's the reason why we don't see it. And in fact, this is also the reason why the bottom part here of M87 is brighter than the top part. It turns out that this bottom part is moving towards us. The gas around M87 is rotating at very high speed. This part is approaching us, and this part is moving away from us. And that's why we see this part brighter and this part dimmer.
So my answer is almost same as Lauren, but the jet direction, you can see the map. The jet ejected to the right direction, but in reality, the jet coming to us, the inclination angle is about 17, like that, maybe, or 20 degrees. So it almost coming to us. But if we see the picture, then it is projected to this plane. Then we can see that ejected to right direction. But in reality, it's coming to us. Yeah.
Thank you, Lauren and Fumi. I'll do my best to translate. There's a lot of information. OK， 我用中文。所以刚刚Lauren 跟Fumi他们的说明是说，我们这边只看到一个方向的喷流。那其实是因为，如果可以借这支麦克风。OK。所以黑洞的喷流，我们想象其实应该会有两侧，对不对？但是对 M87来说，它其实刚好是像这个样子。那朝向各位听众呢，其实像我们听救护车的声音一样，就是跟我们相对接近的内侧会变得更明亮，远离我们内侧会变得更暗淡。所以刚好是这样的几何的关系，所以我们只看到一侧的喷流。那其实我们观测上其实也有看到是两侧的喷流，这跟几何有关。那刚刚另外，Lauren 跟Fumi有提供另外一个资讯是说，为什么我们这个看到这个像甜甜圈的这个样子，它会有一侧比较亮？其实跟这个它的黑洞的旋转轴有关。其实这个喷流它的方向大概也是黑洞旋转轴的方向。所以当喷流这样是这样的方向的时候，代表黑洞它的旋转轴可能是这个样子，或是这个样子。那其实理论上我们经过一些验证之后，我们知道它是这个样子转。那大家看说，如果黑洞的旋转方向是这个样子转的话，是它的下面是朝向各位大家而去，会变得比较明亮。所以这个甜甜圈它的下面会比较明亮，也是类似的原因。所以为什么看到一侧的喷流，然后我们只看到这个甜甜圈的下方比较明亮，其实都是因为旋转的关系。那我们这边讲的旋转，甚至是讲到时空的旋转。那因为黑洞它的旋转会让时空一起旋转。
大声一点。
比太阳还要大的星星死掉会变成黑洞吗？
If we have a star more massive than our sun, so after it dies, then would it become a black hole?
Thank you for great questions. So, if the sun dies, then we will not have any black hole at the place of the sun. If sun dies, then they will be darkened and the atmosphere is expanded and become cold, and that's it. But if we have the very big massive sun, so 10 or a few tens times of the mass of the sun, then if the big sun died, then the big sun will explode, and then the black hole will remain at the center of the atmosphere, after the explosion. But our sun will not become the black hole. That's the answer.
Okay. So you have a consistent
Thank you.
为了证明要我拿钱，对，所以这个我会的我在翻译，然后我不会就交给补红译，对，好。这是很好的问题，所以刚刚傅明老师有特别称赞你，他觉得这是一个很好的问题。第一个就是你不用太担心，我们太阳如果死掉的话，不会变成黑洞。通常会比太阳重很多的恒星才会变成黑洞。刚刚傅明老师没有用因为你还小，你不需要记太精确的数字啦。他说要数十倍给太阳质量的，就比太阳重几十倍那种。它死掉的时候是非常激烈，它会爆炸。哦，你可能有听过叫超新星爆炸。它爆炸之后，它就很有可能中间是会留下黑洞的。不过它最后有特别跟你说，我们太阳不会变成黑洞。好，所以你不用紧张，还是要乖乖上课这样子。I just told to him, okay, don't be worried. We won't have the black hole near to us.
So I heard when you enter a black hole, your cells get stretched and you turn to like a spaghetti. But don't you just straight up get disintegrated if you even get close to it?
Yes. So indeed, what happens is when you get very close, if a person would get very close to the black hole, the gravity is so strong in the black hole vicinity that the force on your feet would be stronger than the force on your head. And so you would start to become a spaghetti, right? You would feel a force stronger on your feet than your head. And in fact, you're right. If you would very quickly become disintegrated, you would become so long that you would no longer be a human being or even a spaghetti, right? You would become completely disintegrated, yes. But this is called spaghettification, this process of being elongated because of the force of gravity.
We still need to translate the fraction to others. Yeah.
Thank you, Lauren, and the question. Yeah. 所以刚刚小朋友的问题是说，当我们接近黑洞的时候，是不是身体会被拉长？那Lauren 是说是的。那会被拉长的原因是，其实当我们很接近黑洞的时候，比如说我们可以想象我们的脚，假如是比较接近黑洞，头比较远离黑洞，那么脚受到的重力和头受到的重力，其实就是我们说的潮汐力会不一样，所以会让我们的上下方向被拉长，可是其实左右方向会被压缩，所以看起来就像是一个意大利面。那甚至英文有一个词叫 spaghettification， 对，它是一个很特别的词，专门是为这种现象所描述的词。那稍微补充一点，这个效应其实是对质量越小的黑洞越重要。像这种超大质量的黑洞，我们在它的事件世界附近很接近它的时候，其实它的效应没有那么重要。那原因是因为黑洞长大1倍，那它会变胖2倍。就刚刚傅敏他给大家看的公式里面，可以看到，我们的 m 增加1倍，其实它的变胖的程度，就它事件的大小会变2倍。所以反而是越重的黑洞，你接近它的时候越不容易被扯碎。可是比较小质量的黑洞，接近它的时候就要小心被扯碎。Thank you, Lauren.
Okay.
我想要问说，现在我们的网络科技已经普遍了，可是为什么还是要用飞机这样来传输我们的？对，不是用网络传输。
Why not use the internet? Why you would need to use the airplane to transport all the data? Yeah, it's a really cool question. Yeah, so you're working for the internet, so that's why you want to know it.
Yeah, so good question. So if you'd like to send a photo to your friends, you use internet now, I think. Yeah. But in our case, it's too large, too huge data. So we cannot send the data via internet. How long will it take if we try to send the internet? I don't know. I have no idea. So oh. 1 year, yeah. So airplane is fast. So yeah, thank you.
The director of the institute of the project once said that you cannot have more bandwidth than a Boeing 747.
787, the Airbus is from your country.
Or an Airbus, whatever.
没有啦，它其实道理很简单。我还不记得你们刚刚有看到一个 slide， 他说其实 EHT 有这么多望远镜，其中有个望远镜是 LMT， 其中的一部分 data 就是 0.5 PB。你们知道 PB 的概念吗？对对对，这就是仔仔马上就可以回答出来，就是对，1T 是1024G 嘛，对不对？然后我们的随身碟现在有1T 的，然后1P 是1024T，1024 Tera。它有10几个望远镜，2017年就有8个啦。但是一个望远镜的随便的一个观察数据就将近是1 PB， 所以你不可能用传 Internet， 你这样传大概会被其他的国民给骂死，因为你一传之后大家都不能用了，对。所以那个楼红有说他们的 PI 又讲，其实那个波音747频宽是胜过那个网络的这样。还有问题？好，我们先让前面的这位好了。
我应该不用麦克风。
好，没关系，那就大声。
对，就是如果说就是那种大质量的恒星死掉会变成黑洞的话，那黑洞再下去会变成什么东西
So, for massive stars, when they die, they can form black hole. So how about even more massive stars when they die?
应该都是黑洞之后会变成什么 ？What happened if the black hole like develop and over time and what does then how will it go and I mean what does it
Yeah. So as we said, these at the end of a massive star, so it could be 10, 20, maybe 50 solar masses star, you can form a black hole. But it happens that there are no stars that weigh 1 million solar masses. There's a limit, and the limit is about 100 solar masses. There are no stars more massive than about 100 solar masses. The reason is because if these stars existed, they would explode immediately. They would be unstable. So, thank you. So, as a consequence of this, the most massive black holes that form from this mechanism are maybe 20, 30 times the mass of the sun, no more than this. But then what can happen is that these black holes merge together. And so from 2 black holes, each with 30 solar masses, for instance, you can make one with 50. And then with 2 with 50, you can make one with 80. And then you can make bigger and bigger black holes. But it's still much less than the black holes at the center of our galaxy, which is 4 million solar masses, or M87, which is 6 billion solar masses. So the truth is, we don't really know how these very massive black holes are formed. One theory is that initially there were many very massive stars, maybe 100 or 1,000. Each one exploded and formed a little black hole, and all of these black holes merged together. And this formed maybe a 10,000 solar mass black hole, and then it started to accrete material. It started to, swallow gas and stars, and little by little grew to the very high mass that they have now. But it's still an open question exactly how these are formed.
So if one star, when the star becomes a black hole, then it doesn't change, like it won't change from black hole to other, I don't know, some atmosphere or something like that.
No.
Just the black hole is the end of everything.
Exactly. Once the black hole forms, that's the end. There is no going back to being a normal stars later. It's a black hole forever. There is an exotic mechanism by which black holes can lose mass. but this is very, very, very slow, and it's not efficient at all for massive black holes, precisely. So massive black holes, they will remain black holes forever. Yeah.
Black hole never change to white hole, right?
No. Once they are black holes forever.
Okay, thank you.
Thank you, Robert, and thanks for the question. So I will translate. I'll do my best. A lot of information again. 所以刚刚听众的问题是说，黑洞成为黑洞之后，它会不会变成其他东西？那答案是不会。黑洞成为黑洞之后，它就继续是黑洞。那刚刚 Lauren 有提到说，黑洞变成黑洞之后，它其实也不会分裂成小的黑洞。那它可以透过合并的方式，比如说刚刚福米在演讲中有提到说，黑洞跟黑洞可以合并长成更大的黑洞。那刚刚也有提到说，在投影片里面有介绍说，比较重质量的恒星，它们在最后，我们刚称说死亡，就是它们没有办法产生核反应，所以它重力塌缩变成黑洞的这个过程里面，其实它还是有一个目前观测到有一个质量的上限。那这些，所以换句话说，这些黑洞它们生成之后，它们大概就是几十个，最多几百个太阳质量。那怎么会长到像我们刚刚提到这些有几十亿个、几百万个太阳质量的黑洞？那它们其实很有可能就是从小黑洞开始，跟各位小朋友一样，吃东西才会长大，要多吃东西，然后吃东西经过合并的过程，慢慢长这么大。那刚刚罗伦还有另外再提到一个，那有理论就是说黑洞它其实会用很慢的方式让它减肥，可是这个减肥的方式非常的对他们来说不是很有效率。那这个方式怎么造成的是，其实就不在我们今天讨论的广义相对论这个理论，它包括了另外一个大家可能有听过的量子理论。但这个效应对我们天文学家看到这些黑洞来说没有那么重要。所以换句话说，就是这些黑洞它们长胖之后，那些减肥的方式对他们的效果都不大，所以黑洞成为黑洞之后就继续保持黑洞，
所以就继续放下去，就不用减肥。我们先问一下后面的，好，刚刚有男生那边好，还是你就大声讲没关系，我怕那个麦克风会直。
How do we measure the mass of a black hole?
So how did we measure the mass of the black hole? So in case of Sagittarius star, we can measure the black hole mass very precisely. Wait a minute. Here. So we can measure the motion of the star. Then we can calculate the by the Kepler equation. Using the Kepler equation, we can estimate the mass of the center object by measuring the motion of the stars. Yes. And in the case of M87, a little bit difficult, more difficult than this case. So sometimes we measure the gas motion, estimate the gas motion around the black hole and the center of the galaxy. Then we can estimate the black hole mass. So before the imaging of black holes with EHT, we do not know the exact number of the black hole mass of M87. One team measured the black hole mass at the 30 billion solar masses for M87, and the other team measured the black hole mass is 60 billion solar masses. So which one is correct? We did not know that before the M87 imaging. But after the EHT observation, we know that the larger mass, so 60 or 65 billion solar masses is correct. We knew that. Yeah. Do you have any? Okay.
No, go back to the assholes.
好，那我翻译一下富敏 ，Thank you 富敏，刚刚的回答。那简单来说，其实还是用重力，那譬如说，大家想象我们的
我来表演。
好。我本来想说你当黑洞的重。
黑洞用质量比较大。
好，各位小朋友可以想象，譬如说冰微，它是一个有质量的东西。那假如冰微缩成一个点的话，它自然就变成一个黑洞。可是对我来说，我在很外层在绕这个质量的时候，我不会因为它的体积的大或小，我不会因为它是冰微现在的状况，还是它变成一个黑洞，而受到它的重力有所影响。所以我们可以透过黑洞在它的能力所及的范围里面，比如说冰微，我站在这边，我可能受到冰微的重力的影响。可是如果我们站在10个接口之外，那我受到的影响可能就不是冰微了，而是其他所有我跟冰微之间其他东西的影响。所以在冰微它的质量所及的范围里面，我们可以观察它周围的东西怎么绕。那有什么东西会绕着黑洞呢？譬如说黑洞周围因为重力束缚的星体，那另外一个就是在黑洞周围被重力束缚的气体。那2种方法都可以让我们估计冰微的体重。那其实，在 EHT 的观测之前，的确有2种方法，一个是根据星星的运动，然后一个是根据气体的运动。他们得出来的结果，估计 M87中心这个超大质量黑洞的质量刚好差2倍。那我们 EHT 的结果是跟其中一个比较符合，所以 EHT 我们看到黑洞的同时，其实我们提供了一个新的方法，能根据黑洞它影像的大小，因为这个影像的大小，它的这个阴影的大小会跟它的质量有关，我们的最后的结果是跟其中一个是相符合的，所以刚好是一个独立的方法来知道黑洞它多重。所以还是一样，是我们要回归到重力，在很远的地方，其实牛顿的重力的概念，或是刚刚富明有提到科普勒定律，其实就是根据用牛顿定律来理解，就已经很足够了。
好，还有没有问题？我们让这边好不好？我们再让这边，我们下次再 Q。来，好，没问题。
这个海洞跟虫洞，现在有没有被证实
？OK，they want to know the white hole and wormhole. The white hole and wormhole because we found it or not.
So if you have a theory, right? So for instance, general relativity, it has certain solutions, right? Certain objects that kind of exist in that theory. So in the case of general relativity, there are many possible solutions to the equation. One solution is a black hole. So that's one object, one kind of object that can exist with general relativity. They are not the only ones. There are other more complicated solutions to the equations of general relativity. And then you can also find other theories of gravitation, which maybe it's my phone.
No,
my phone. So there are other theories of gravity that can be invented, right? And that would have other solutions, different solutions. So, for instance, white holes, wormholes, these kind of objects, they are hypothetical solutions to these equations, okay? So they could exist. We don't have. Oh, no problem. So these objects could exist in general relativity or in other theories of gravitation, but they have not been found so far. And in fact, so one of the reasons why it was so important to make this image, or these images, was to see, because so these objects, they could exist, but they would look different. There are other kinds of objects, yes? So by looking at what exists in the universe, you can hope to find one class of object or another. So what we have found at the center of MMT7 and Sagittarius star looks like a black hole. It looks exactly like what we expect a black hole to look like. So the simplest solution is that it is a black hole, okay? But it doesn't mean, it could be something else, or there could be other kinds of exotic objects in other places of the universe. We don't know that yet. But at the moment, we have no evidence that these other objects exist. They are theoretical constructions, solutions of equations, right? We don't have any empirical evidence that they exist.
Thank you, Lauren. 那谢谢刚刚问的问题。那一样有很多 information， 我试着尽量翻译。那第一个是听众问的是说虫洞、白洞是怎么一回事？那其实我们先分两个角度来看，一个是在刚刚富米有提到的广义相对论这个架构里面，它描述了时空会怎么样弯曲。那这个时空怎么样弯曲，它有一个限制。那在这个限制之下，我们可以有很多种不一样的时空弯曲，黑洞只是其中一种。所以刚刚提到的白洞、虫洞等等，是其他可能弯曲的方式。那时空会怎么弯曲，其实会跟它所需要的能量有关系。那大家可以想象说，如果天文学家在宇宙中没有发现很类似是黑洞的东西，其实天文学家也不见得会对黑洞有兴趣。那很奇怪的，非常奇怪。如果我们大家停下来想一下，这样子奇怪的时空结构，我们刚刚说黑洞有一个事件世界，这个事件世界它是一个虚拟的表面，用光来定义的。任何东西进入这个虚拟表面之后，它再也逃不出来。这样的东西真的存在吗？所以跟大家一样，早期的物理学家、天文学家也不相信有这样的想法，包括爱因斯坦。那直到天文学家认识到，在宇宙中有很多天体，它的最可能的本质是黑洞，那大家才把注意力转移到很认真研究黑洞真的存在在宇宙中的话，它会有什么特性？那目前发现这些特性就跟那些天体它展现出观测的特性一样，但是目前为止我们没有发现一定要用白洞、一定要用虫洞来解释的天体，所以应该是反过来，天文学是一个观测科学，我们关心看得到的。那天文学家他想要问的问题，反而是说黑洞它如果真的存在在宇宙中的话，那它对宇宙会造成什么样的影响？那比如说像 M87这个黑洞，这样的喷流，在观测之前我们就觉得它的这些喷流的源头，它应该算是一个黑洞。那如果它真的是一个黑洞的话，它看起来会像是什么样子？那的确跟我们根据广义相对论告诉我们的线索，它看起来会有点像是甜甜圈，中间暗暗的，那看起来真的像是这个样子。那这是第一个部分。那刚刚 Lauren 也有提到说，那其实黑洞它有没有可能，我们现在对黑洞概念只是一个替代品，它有没有可能它其实也不见得有我们刚刚说事件世界的这种特性，而是一些其他可能的物体，有可能，但是我们目前我们对黑洞的认识，至少广义相对论带给我们对黑洞的想象，是跟我们目前的观测是相当符合的。那的确有物理学家、天文学家在研究说，假如黑洞不是我们刚刚想象的广义相对论带给我们那样的架构底下的天体的本质的话，它会有什么特性？那如果我们可以对这些特性做出预测，那我们将来会有更精细的观测的话，那我们很高兴，那在未来我们就有机会进一步验证黑洞是不是我们想象中的黑洞，还是其实它是一个近视。好，这是简单的 translation。
好，我给这位一点机会，好，来。
Sorry, I have too many questions today, so I just I just choose one. So my friend found that all of black hole pictures of about 2 black holes are in red, yellow, and orange. There's no green and blue in the pictures. Is there any reason in that, or it's just a coincidence?
They prefer another color. Maybe rainbow color.
So, no reason.
No reason.
Yes, no reason. We observe radio waves, 1.3 millimeter radio waves. And red color is a kind of, I forgot the exact number of 600 nanometers. Yeah. So the color has no meaning. So we can make a blue colored black hole image, green colored black hole image. We can, but I'm not sure how we decided, but but no means. So we can use any color for black hole. So you know the electromagnetic waves have the wavelength for the colors, and if the visible light, then the wavelength is decided depends on the colors. So the colors decided depend on the wavelengths, and longer wavelengths became infrared and radio wave. So we observe radio waves, so longer wavelengths than visible light. So, but we cannot make any images with invisible light, right? Yeah. You cannot see them. So, to show the image, we use exact color to show, just to show the image. Is it okay? Yeah? Okay. So this is my answer.
Thank you for me. 所以刚刚听众的问题是说，他跟他的朋友发现了我们2个黑洞的影像都是橘色的，这是什么巧合吗？我们有没有发现其他不同颜色黑洞？那其实是因为我们的黑洞影像它是电波的讯号，还记得吗？我们是用干涉仪的方法，电波讯号这些影像中比较亮、比较橘的部分，只是代表那边的讯号比较强烈。因为我们并不是用可见光，这已经不是可见光讯号，所以我们只是选择一个颜色，然后在比较明亮的那部分，就代表说那边的讯号比较强烈，只是这样子而已。我们完全可以把它做成其他的颜色。
所以你们在看气象图所有类似的概念啊，就是我们看到雨量什么，那都红外线观测，但是你怎么知道红红的就是雨量比较多，蓝蓝的就是温度比较低，类似这样。所以其实我们早就习惯用颜色来帮助我们去区分一些不可见光的一些表现。所以如果哪天你变成天文学家 ，when you leading an EHT team afterward, you can just give a policy, say, I don't like the orange color. I want to change it to, I don't know, for the light pink or lime. It's up to you. So 这没有关系的。我们看好这边中间一点好。来，我们这个女生好，对 ，the big lady because you have to come here。来，好，有，好，麻烦你，谢谢。好，来。
Thanks for giving us the amazing presentation tonight. And I have some questions for imaging strategy of M87. The first question is, why should imaging members be divided into 4 teams? And the second question is, all teams agree on the ring-like structure of the you present in the slide of the 4 pictures. And the similarity is they all look like a ring. And I want to know, on the other hand, what's the reason of the difference between these 4 pictures? Is the is layer imaging from different algorithms, or what's the reason of layer difference? And the third question.
No third question. Okay. I think second question is a limitation for each individual. Okay. Because okay. I think you.
I will let Fumi answer the questions because she was on the imaging team. But I just want to say that in the EHT, even our snowmen are yellow and red. So everything is yellow and red.
I don't understand the second question. So I will start from the first question. Yeah. The reason why we have 4 teams for MAT7 imaging. Yeah. Yes. So if we are one team, so we discuss how we reconstruct the image, which parameter we use, which method we use. Then we can get this image. Oh, it looks nice. Then this should be published. But this is the first black hole image in the human history. So we would like to check very, very, very carefully whether the image is correct or reasonable. So it's better to divide the teams, and if we have 2 teams, then we can double check without any exchanging information between these 2 teams. Then we can double check for the image. So if we have 3 teams, triple check. And if we have 4 teams, what can I say in English? Quadruple checks. Okay. So if we have many teams, then more teams are better. But we limited number of members in the imaging team, so we choose 4 teams to divide. That's my answer. For first question.
The second question is actually, what's the difference of these 4 images?
Yes.
Are they from different overall?
Okay. So these 4 images are a little bit different, you see. Yeah. This is caused by the method of imaging. So that maybe different imaging tool we use, or maybe we use different imaging parameters. So we have at that time we have 3 tools for imaging, and each tool have many parameter setting. So if we choose same imaging tools, even if we use same imaging tools, we can many choices to make image. So parameter setting. So these imaging difference, one thing is difference of tools, and one thing is difference of imaging parameters. Yeah, this is my answer.
Thank you, Fumi. 所以刚刚听众的问题是说，为什么要分成4个小组？那原因是因为这4个小组用了独立的方法，那这些方法里面各自有各自的参数，那所以这其实是4个不同的方法，然后各自找到最适合的参数所得到的结果。那他们在做的时候，其实4个小组的成员是不能交换意见，所以就完全不能不小心看到对方的图，然后你自己心里就有一个想法，做出跟对方类似的图。那如果大家还记得，这是第1张黑洞影像，所以我们好像会很期待说跟我们心里面预测的一样，但是会不会因为我们太想看到一个甜甜圈，我们就真的分析出来一个甜甜圈？所以要怎么避免这件事情？那第一个是把它分成4个独立的小组。那其实另外一件事是，其实刚图米好像也有稍微提到，那其实在做这4张分析，这是真正的观测的资料，在 我们这4个小组，在对观测资料做分析之前，他们还用他们各自的方法验证说，我们已经知道答案的那些假设观测的情况下，是不是我们可以得到跟我们知道答案的结果？比如说刚刚的雪人就是其中一个，我们只有做的人知道他的答案是一个雪人，但是在这4个小组都不知道答案是什么的情况下，他们是不是都可以得到类似雪人的图案？所以这4个方法都是已经经过验证，我们有信心说它是一个有效的方法的时候，才把它用在观测资料上。谢谢。
好，最后一个问题，因为其实我觉得大家问问题还蛮踊跃。最后一个问题，我想问过的我就可能不会点了，所以来 ，the last one， I just OK。哦，这样我压力有点大哎。我到底要选谁？好，你有推荐的，所以恭喜你。好，你问最后一个问题。
Thank you for your speech, and I want to ask because the black hole is so small in the sky, and how do scientists to decide where to find the black hole?
Okay, so we knew because of So, for instance, in the case of Sagittarius A star, we know it's at the center of our Milky Way, and we know where the center of the galaxy is located, and we know that these stars are moving around, a certain point here. They are all, if you see that they are all little ellipses, little oval shapes, and they are all moving around a certain point. And that point is where the center of the galaxy is. So this is where the black hole is located. So even though it is very small, we know exactly where it is in the sky. Right? So that's how we know where to point the telescopes. And the same is true in M87, right? We know that the black hole is exactly here at the center of the galaxy. We know exactly where to point the telescopes because we know exactly where it is located.
所以简单的说，这边刚刚介绍 M87 还是我们银河系中心的黑洞，其实我们知道它的质量，我们也知道它的距离，所以其实我们可以估计它在天空中的夹角是多大。但是其实我们知道质量和距离的黑洞，在宇宙中不止这2个，所以简单的说，是我们可以把所有已经知道质量跟所有知道距离的黑洞，把它列一个表。那在第1名和第2名就是 M87。星系中心的超大质量黑洞跟我们自己银河系中心的超大质量黑洞，那大家可能会发现一件事，就是恒星级质量的黑洞都不在这个名单上面，因为它们太小了，对不对？那只有这些胖胖的黑洞，它是几百万、几十亿个太阳质量的黑洞，我们才有机会用目前EHT 可以达到的解析度观测到。
不是最后帮你做个结尾，就是我们找黑洞并不是凭空乱找，就说那边我猜有黑洞，让我来看，不是，我们早就已经有就是候选名单了，就像刚刚卜宏一老师讲的，就是说，就像我们已经有嫌疑犯了，我很喜欢用罪犯的方法来形容天文学的发现这样子，那这很好懂，就我们有嫌疑犯，只是我找不到他的最终的指纹，类似那种概念，那 EHT 的 image 就像你找到指纹。但在找到指纹之前，你可以有他没有不在场证明，或者他有犯案动机，或者他有一些人证，就已经有这些人存在了，所以你才会把它列成所谓的重大嫌疑人。那 M87跟银河系的黑洞早就是 我们早就是觉得他是我们要看的重大嫌疑人了，只是随着我们的机器更好，然后我们有更好的设备，那我们终于可以直接去看他们的影像，这样子。
所以换句话说，我们想要找最胖、最近的黑洞，那我们把这两个资讯都结合在一起，那最胖、最近的黑洞就是这两个。
对。好，我觉得我们还是，其实我还蛮高兴，因为其实大家都问答蛮踊跃的。其实我甚至都觉得说，是不是我们一开始就直接用问答就好了？所以，但我很高兴大家都其实很踊跃。但是不要忘记了，我们这黑洞的展陆续每个月都会有演讲。那我忘记，我刚刚有点失礼，我忘记介绍我们卜弘毅老师，他其实也是我们 EHT 的 member， 跟老洪跟夫冕都是一样的，他也是台湾代表之一。所以我特别请他来翻译，以免我乱讲。OK。然后左后方有一个看起来好像怪叔叔的，就是 Satoki， 他也是我们刚才讲的 GOT 的算是负责人嘛，对不对？很重要的 project 的 leader， 然后他也是我们EHT的。好。这只是我们第2场演讲，我们后面还会陆陆续续的演讲，那包含像 Satoki、卜弘毅老师，因为我们会展到明年，所以有机会会看到他们的主场讲他们的一些东西。那我们今天就先到这边，也谢谢大家。好，我们最后来帮2位讲者，有个热烈鼓掌。